I was requested by some of the organizers to give a survey of arithmetic applications possible and present of automorphic forms. So let me begin by saying we've heard a lot about that we hope to learn about zeta functions first of Shimura varieties, or maybe one should say associated to Shimura varieties, so that one, for example, allows higher weight representations. From these, one might hope to learn about zeta functions associated to all varieties, just as from zeta functions of modular curves, you hope to learn about zeta functions of all elliptic curves. And finally, just zeta functions of these suitable Galois representations. And one hopes to know that these have analytic continuations and functional equations in suitable cases, and that they're automorphic. Well, of course, these are arithmetic applications of automorphic forms, and basically these have been the progress, at least with the third one, was described by Chris Skinner in his talk. And what I want to do is to explain, what I'm supposed to do is explain some of the progress that one might hope to make beyond this in arithmetic. That is, using the L functions, what one knows about them from the automorphic side, what one can use about them in arithmetic. Let me just say first that a more interesting talk, if more speculative, might have been the other way around. What are the applications of arithmetic to automorphic forms? And it seems to me that in this conference we've heard a lot about how you use trace formula, and especially one has the fundamental lemma, had to mention that, to prove some of these results. But it's been, I think, very clear for several years to people who approach this field from a more arithmetic point of view, that in fact arithmetic will probably be essential in establishing some of these. One has only to think, for example, of one of the standard tests Langlands likes to give for his theory in functoriality. Can one do symmetric powers, say, of a GL2 form? It seems to me that the most natural way to do this, at least for a holomorphic form, would certainly be to show that you have a relation between Galois representations and automorphic forms, because you can always take a symmetric power of a Galois representation. And as, if you like, as evidence of this, you see in the function field case that thanks to Laforgue's work, of course, you can make a symmetric power lift in the automorphic side. I don't know how much of this was known before you had an equivalence with Galois representations, but it does seem to me that arithmetic will have a lot to offer precisely in the cases where the trace formula seems more difficult. Okay, but my talk is going to be less speculative, and I want to talk about what one can hope to learn in arithmetic from knowledge that the zeta functions are automorphic. So these come down to this, what we see at the moment, to an understanding of special values. And there have been many conjectures over the years, Birch and Swinnerton Dyer, Stark, Tate, many others, Deline, Valenson, Locke, Cato, and so on. Lichtenbaum, I should put. I'm going to concentrate on Birch, Swinnerton, Dyer, but before I do that, let me just talk about something that's might see some powerful applications when combined with Arakelov theory. So there is a conjecture, there are many conjectures which are related to the what's called the ABC conjecture. And let me mention one, which is that if you take the Falting's height of an elliptic curve, so Falting's height is the one he introduced in his study of the Modell Conjecture, Falting's height of an elliptic curve should be less than some constant times the log of the conductor of the elliptic curve. So this is a conjecture. Which would have very powerful Diophantine implications. It implies, depending on your constant, a weak or strong form of ABC, implies effective Modell, and so on. So it gives you a great deal that we want to know. And he has proved the theorem. This is why it's related to these automorphic questions, that if you take the Falting's height of the Jacobian of a modular curve, because you know it's a zeta function, you can analyze this analytically, and he proves this is less than g over 2 log n plus little o g log n. And also there's a lower bound of a similar kind, a constant log n. Well, if an analyst familiar with averaging saw this, an analytic number theorist, I'm afraid they would express some skepticism. When you average L functions over characters, if the individual ones were as good as the average, you would do better. You would do things that are not true. There's always a bit of a loss. Nevertheless, there may be special circumstances here. It's only for an elliptic curve, not for a general intermediate abelian variety. But anyway, this theorem stands, as far as I know, as the only really explicit calculation of general abelian varieties in terms of the conductor. Of course, you can compute the height explicitly in terms of the discriminant, and the whole point is to relate the discriminant of the elliptic curve and the conductor. Okay, so let me now turn to Diophantine questions. So for curves, of course, genus 0 is classical due to Hilbert and Hurwitz. And genus 2 or greater, we have Folting's theorem, and the remaining problem is to find some effective version of Modell. First is one possible approach. And the mysterious one is genus 1. So if we have, let's assume we have an elliptic curve, Wiles. We can put in Weierstrass form. And now with rational coefficients, y squared x cubed plus ax plus b. Then we can form the L series, product of 1 minus ap p to the minus s plus p to the 1 minus 2s inverse, and let me just take primes not dividing twice the discriminant of the cubic. Then the conjecture says that C of Q, which is known to be an abelian group, finitely generated by a theorem of Modell. Well, so this is the theorem, that C of Q is z to the g plus some finite abelian group. And the conjecture is that at s equals 1, the leading there is the Taylor expansion begins C s minus 1 to that power g, giving the rank of the elliptic curve. Well, we now know that LCS, you will know, is the L series of a modular form. And it's natural, in fact, to take a new form associated to F. So let me call this F0, FC here, and then I could take a new form F associated to FC. And then the refined conjecture would actually give you a precise formula for the new form that is, so these two forms differ by a finite number of Euler factors, and here for this one expects a nice formula for the CF. This one can for the C2, but CF is supposed to be the order. So this is the refined conjecture. CF is the order of the Tate-Shafrevich group divided by the torsion group squared, and then there's some periods one to infinity, and then for the bad primes, and then a regulator term, which is a determinant of a height pairing on a basis of the points, the rational points. Okay, so once you know that the form is automorphic, one can hope to get more information about this conjecture, and indeed that's what has happened. So originally the work on this was mostly on the CM case. So myself, Coates, Rubin following methods of Kolyvagin. CM case is for a small number of families of elliptic curves, such as y squared is x cubed minus dx, y squared is x cubed minus k. And then what was called the modular case, but of course now is the general case, due to first big breakthroughs due to Gross and Zagier, Kolyvagin, some refinements now due to Kato, and this general case has been generalized by Zhang, and I want to explain a little about this now. So the main results, so the main theorem in this earlier work due to Kolyvagin was that one could summarize if either the L series is non-zero or the derivative is non-zero, then the first conjecture was true. And also there were refinements that the refined part, essentially the idea was that one could get a bound, not be too precise, upper bound on the order the Tate-Shafarevich group in the two instances described, so under the same hypotheses if L1 is non-zero or the derivative is non-zero. So that's a good upper bound. In the CM case, this was taken further by Rubin. That one gets, at least at many primes, construction of elements of Shah, in other words, so let's say construction of P part of Shah for any P. But this is still missing. The upper bound is still true in the general case, but the construction is missing. It's the one part where the general case lags behind the CM case. All this is made possible by the fundamental method idea of Gross and Zagier, which I'll come to in a moment. Let me just say that the part of Kolyvagin and also Kato was to use a notion of Euler system, which I'm not going to describe. To the best of my knowledge, there are 5 Euler systems that are known: Gauss sums, cyclotomic units, elliptic units Heegner points, and then, so these were somehow, when he defined the notion, were somehow the immediately apparent ones. The subtle one, the new one due to Kato, are Euler systems in K2 of a function field of modular curves. So it's K2 of function field F0n using Siegel modular units. And this was motivated by construction of Beilinson. And it's very automorphic, and one would be very nice to see generalizations of, more cases of Euler systems. Each of these gives very powerful theorems in the arithmetic context in which they occur. But as yet, no one, as far as I know, has managed to construct other Euler systems. But since the Euler systems seem to be related to special values of L functions, which in turn are supposed to be automorphic, one might hope that an automorphic construction were possible. Well, Kato's method enables one to analyze the elliptic curves in cyclotomic towers. The method of Gross and Zagier, which I'm coming to now, enables one to analyze them in anticyclotomic towers. And for now, the Gross-Zagier one is the most powerful. And I want to review it before I explain Zhang's generalizations. So the situation is the following. We assume we have an elliptic curve to start with, and a modular curve mapping to it. And we fix this. We choose this map in such a way that if we have an x in the curve, it goes to the class of x minus infinity in the Jacobian, and then to E. So this commutes. In other words, we pick a map pi such that infinity, the cusp infinity, maps to 0. Then there's a construction of points on x0 of n as follows. So you pick an auxiliary imaginary quadratic field. In which n splits. That is, all the primes in n split. That's right. We find an ideal n in the integers of k with the property that OK mod n is z mod nz. And then we have an elliptic curve we can define an elliptic curve by C mod the lattice OK, and this has an isogeny to C mod the inverse of n, and it's known that this CM elliptic curve, this pair of CM elliptic curves, corresponds to a point on x0 of n. x0 of n classifies elliptic curves with an isogeny of degree n. This is an isogeny of degree n for this elliptic curve, C mod OK. And classical theory of complex multiplication says that this point is defined over the Hilbert class field H of K. Okay, one can generalize this construction a little. One can write OC for the ring Z plus COK, and then consider C mod OC to C mod NC inverse, where NC is N intersect OC. And again, the theory of complex multiplication says that this gives a point in x0 of n over the field HC, which is the ring class field associated to this order. And to make precise that, we're not going to use that for the moment, but now to state the theorem of Grocery. So we have an L function associated to the elliptic curve, and we also we want to consider the L function of the elliptic curve over K, over this auxiliary imaginary quadratic field, which factors as the L series over Q times a twisted L series, twisted by the character chi of K over Q. And the theorem is that, first, that the L function vanishes in this case, and that the derivative is equal to a non-zero constant times the Néron-Tate height of, this is Néron-Tate height of a certain point on the elliptic curve. So the height, the point in question is as follows. So you take this point, I should have called this one, I'll call x of c. The top one's x of 1. So we have this point x of 1. Well, first we want to map it down to e, so we take pi of x of 1. Call that y1. That's a point on e, but it's still only defined over h, over the Hilbert class field. So now you take the trace from h to k of y1, and that's the point. Well, pk depends on the field k. So the derivative is a constant times non-zero constant which is completely explicit, times the Néron-Tate height. And the Néron-Tate height has the property that if the height is non-zero, then the point is not a torsion point, if and only if. So if the derivative is non-zero, one constructs a point of infinite order here. And it's easy to deduce what you want about the elliptic curve over Q from knowing it over K. Okay. So this is how the theorem will be stated from the point of view of arithmetic. But one of the main insights of Gross was that you actually, what you're computing is not the L series of E so much as the L series of a Rankin-Selberg convolution where you take the L series of, well, one way to put it is the following. So if I take automorphic L series, so I normalize them differently, central value at a half, it would be the derivative at a half. Maybe put s minus a half of the convolution of pi f. So f is the modular form that corresponds to E. With a theta series. So theta, I shouldn't put theta chi, let me put pi chi. So if we start with a character of the Galois group of k bar over k, with the property that complex conjugation acts on it like -1, it's an anti-cyclotomic character. That means if you lift the action of the Galois group of k over q to the Galois group of k bar over q and conjugate chi, you get its inverse. Then you induce chi. The L series of chi viewed over k, so the L series over q of in chi, is the L series of a theta series, or let's say of something automorphic over Q. We'll call that pi chi, and then you take the Rankin-Selberg convolution of pi f and pi chi. This procedure works, doesn't have to assume that you have an elliptic curve here. This works also for any f on gamma 0 of n, and gives you information about a certain abelian variety contained in the Jacobian of x0 of n, which will not be an elliptic curve in general. So this gives similar theorem for an abelian variety one calls AF contained in the Jacobian of x0 of n. So the insight of Gross was first to see that this is really something you should view as the Rankin-Selberg convolution. That is, the naive thing to do would, of course, be just to look at the L series of the elliptic curve over Q, the original elliptic curve, analyze its derivatives. That's the wrong thing one wants to do, make this automorphic construction, analyze its derivative. And the feature he saw was special to this was that for this whole family of characters, the root number was always -1. And it seems to be an open problem, except in the case that I'm now going to describe of Zhang's, to find other such families where one might hope to compute derivatives, because you have a family with similar properties. Okay, so let me discuss Zhang's work. So Zhang, in the first statement of Gross-Zagier, the first thing we want to generalize is to replace Q by a totally real F. And the second is you want to analyze not just this basic CM point, the x of 1, but also x of c, for general c, not treated by Gross-Zagier. And I'll explain later why that seems to be significant. So although I think at the time these seemed like they ought to be quite doable, it's actually proved rather hard to provide these generalizations. And I think part of it, Zhang's techniques that he brings to it are, one is systematic use of our Kaloff theory, and the second is much more use of automorphic theory as it's been developed for Rankin-Selberg convolutions. Okay, let me just state his results then. So we start with F totally real. So degree G, discriminant df. And this time I'm going to start not with a map from x0 of n to e. Let me just start with the form this time. So F will be a new form, weight 2 on gamma 0, some ideal n. This is on GL2 associated to GL2 F. And one has to make a familiar condition in this context that either G is odd or for some prime dividing the level it only divides it to the first power. That ensures that you can find, under the Dirichlet-Shimizu Jackie-Langlands correspondence, you can find a form associated to F on a Shimura curve. Okay, then we use the same setup as before. So we want to take K, totally imaginary quadratic extension. Character omega. Omega is the character of this extension. We want a character also an anti-cyclotomic character, so that's a character of AK cross, trivial on AF cross. And as before, you can view this, the L function of chi as the L function of a theta series, or indeed of an automorphic representation of F. And then we can analyze the convolution so I think to normalize it, I'll say L S minus a half pi F cross pi chi is L S F chi. Okay. Take the theorem. Then the theorem of Jean. So we need to assume, I don't know if we need to, but we will assume the conductor of omega, that's the character of K over F, and the conductor of chi co-prime. And secondly, that if you take D to be the conductor of chi squared times the conductor of omega, some technical condition that if P divides D, then P squared does not divide N, I think. Correct? Like that. Believe. Then one gets the L prime the derivative of the L function again is a non-zero constant times the height of some point. BC. But now I have to tell you where you find this point. So this point, well, under the hypothesis star above, there exists an abelian variety AF contained in the Jacobian of a Shimura curve. The Shimura curve will be its L function will involve the L function of F. In fact, say up to isogeny, well, this determines it. The L function of this abelian variety is the product of the L functions of F and all the other conjugate F's. That means conjugating the coefficients of the form. And the CM point one uses is, well, again, you want to take X to the Jacobian of X, project some way to AF. I'm not going to be too precise about this. There was always a little bit of some mystery about what you should do for this map, because in the original one, we took x, the class x goes to the class of x minus infinity. There are no cusps here, and what you do is you take the class of x minus something which is based on the canonical class. You have to adjust it by elliptic fixed points. If we're assuming no cusps, that's all you have to adjust it by. This is not quite integral. It may be rational, so to make sense of this, you want to tensor with Q. And then what Zhang does, it says, shows that if you take a suitable CM point constructed in this way, then in this formula, the one you get by taking the image and then the trace is the one you put in the formula. Okay, now why do I devote this time to what might seem such a special case, at least when one's talking in terms of the whole program? Well, let me make remarks on this. First of all, as you can see, this works for abelian varieties, some abelian varieties, namely the ones that come from automorphic forms, Shimura curves. One really wants to extend of course, this to abelian varieties in general. For example, for abelian varieties of dimension 2, without any extra endomorphisms, one expects, but I don't think one knows, that this comes from the L function is associated to an automorphic form, and I believe it's supposed to be associated to one GSP4, and one would like then to find, at least to set up some kind of analysis of what might go on in general. Of course, what seems special in the case here, arithmetically, is that you actually have a map from your Shimura curve to the elliptic curve. So the use of CM points on the Shimura curve, or the modular curve, is very easy, as you just project and take the trace. It's not at all clear how one can do anything like this in general. Why is this such an important Diophantine problem? Well, it seems to me, if you have a variety, any variety of a number field, as I understand the conjectures, if the points, let's even say over Q, if the points over F, if there are infinitely many, then the conjectures seem to be, if I understand them, that this only arises because there is a map either from a projective line to V, in which case hopefully you could test it just using p-adic methods, or there's a map from an abelian variety to V, which contributes infinitely many points over a number field. So that somehow this case of abelian varieties seems to be the critical case, or a critical case, in understanding how you construct infinitely many points on general varieties. So it seems much more general than perhaps these specific cases suggest. one would dearly like some construction that didn't confine you to CM points. This seems to be the most, for elliptic curves, this is the fascinating problem. The use of CM points is ideal when the rank is 1. When the rank is 1, the Gross-Zagier formula, the generalizations, show that you can find the points using CM points. But they also show that if the rank's bigger than 1, the use of CM points does not work. So one needs another construction. And it would be nice to think that one could do this automorphically. The cases that have been done are using the Rankin-Selberg convolution seems so elegantly to tie up the arithmetic and the automorphic side that one would certainly appreciate doing that in some generality. But one has no idea how to do this. Failing that, people have made very extensive study of CM points. And this is where there's been also some success recently. So let me just say a few words about CM points. As I say, this is almost certainly not the deepest problem, but it seems much more tractable than the core problem, which is really to understand the higher derivatives and the rank greater than 1 and so on. Okay, there are 2 conjectures I know of about CM points that people have been studying. Let me first mention the conjecture of Mazur. So this is about points on, let me take a simple case. So supposing you take J0 of n, or actually let me take an elliptic curve which sits inside J0 of n, one of these been considering. Then we've seen that you might get CM points by considering these points x of some class C, x corresponding to array class C, and then you took y of C, remember, was so you took x of C, which was on x0 of n, h of C. You projected that to EH of C, and then you took the trace down to E of K. Now, sometimes that's 0. There's nothing you can do about it. So the conjecture was that, okay, you don't go all the way down to K of C. Supposing we take H of P to the n, so x of P to the n here, some power of given prime. And instead of going all the way down to K, maybe you want to go to Kp to the n. So that would be part of the anticyclotomic ZP extension of K. So not all the way down to K, but from the point of view of Iwasawa theory, this is very useful for analyzing even statements over K. Now, it wasn't clear that for all n, this map wasn't 0. So the theorem proved by Cornu and General and Batzal, special case, pointed the way, is that in fact this is non-zero for large n. And hence, what you get, in fact, is an infinite dimensional piece in the Modell V group over the anticyclotomic tower, so that one sees that the CM points actually generate a very big group, perhaps not quite surprisingly, but it took a while to prove. This is from 1983. So the idea is the following. You look at what you really want to do. This is only a finite group, a fixed finite group, basically. You're going from basically a ray class field to a piece of it. And what you want to do is take a finite number of copies of x0 of n, and you want to take your point and then take the conjugates for the action of hp to the n over kp to the n. So look at the images of these points. So r is fixed here in the r copies of x0 of n. Well, the first naive thing to ask is, well, is the image dense? Not just Zariski dense, but really dense. And the answer is no, because if you look at the action of the Frobeniuses that correspond to the primes that ramify in K, there's actually, you can see they satisfy a relation. So there's some obstruction, which you get rid of, and you reduce this, it's like genus theory, you reduce this to a product over the ones that really seem to genuinely mix up the points. And then what you do is, well, you can ask the same question, but in fact what it's better to do is to reduce everything mod some big inert prime Q. And now the CM points are just the supersingular points in characteristic Q. They're very easy to describe. And you can describe the Galois action on them. And this question now you ask is, well, is the image basically surjective mod Q? Or is the image big mod Q? And this turns into a question just in basically in combinatorial group theory, which this was the idea of Vatsal, you can actually solve using application of Ratner's work on Raganuthan's conjecture, solution of Raganuthan's conjecture. The second, I don't know whether these methods would apply to the second, but the second conjecture on CM points is called the Andre Oort conjecture. Which stellar conjecture, which roughly says that if you have a subvariety of the moduli space of abelian varieties, and so this is a moduli space which has lots of CM points, and the question is, in this subvariety, if this has CM points which is Zariski dense in Z, is Z itself a Shimura subvariety in some fairly natural way? So if CM points are Zariski dense in Z, is Z itself a Shimura variety in some natural way, subvariety? Not just a Shimura subvariety, but what's called a Hodge type. So Zhang has proposed a way of analyzing this. So Gross-Zagier applies to the derivative. Gross himself pointed out that you can analyze the L function when the L function doesn't vanish in some ways. And this was generalized by Zhang. And both can, in a sense, be viewed as a generalization of something Duke did, which is that the L value Duke was proving that I think he explained in his lecture, the CM points, how the CM points are distributed just in the upper half plane. Here you want something subtler about the distribution of CM points. And the point of Zhang's extending from just the basic CM points defined over the Hilbert class field to those over ring class fields was precisely to try to apply in this analogous situation an analysis to the André-Oort conjecture. So there are still problems to do even in these CM points, with these CM points, which hopefully some of these ideas will yield.
Questions or comments?
Okay, Mazur's conjecture was that if you take an elliptic curve you look over the imaginary quadratic field K, take the anticyclotomic ZP extension, so this is anticyclotomic, then the use of the CM points I described from ring class fields of the type Z plus P to the n OK for all n, take the trace into this field, would generate in the Modell V group something of infinite rank. And it's enough, in fact, as I perhaps implicitly said, just to prove that one of these maps is non-zero. That's how you do it in the proof, but that in fact implies that it gives an infinite contribution. Yeah. That's I mean, one always expects problems. I have no idea whether that would be a handicap. I think the point about GSP4 is, well, there are two groups that one can and wants to use, the unitary groups and symplectic groups for arithmetic. And for many purposes, for Galois representations, the unitary groups seem better. For some purposes, sometimes for special values and so on, symplectic groups seem better. I don't think it's clear yet which one is going to have the more influence in the long run, but those seem the two most important. And it would be nice to have one non-trivial example of a symplectic group that one could really work with to go beyond modular curves. I mean, as you see, almost everything I've said is based on modular curves and Shimura curves. But as far as I know, for example, even for the symplectic GSP4, I don't know if it's come out of this conference clearly, whether you really have four-dimensional representations where you really understand what the characteristic polynomial is at every place, or at least all but finite, all but the bad primes even. And to try and do arithmetic when you don't have these basic things seems very hard. I'm convinced that they'll both be extremely useful.
No more questions, comments? So we thank the speaker.